This is the fifth video in the forces topic, and it's split into two videos on this page. In this video, we'll be looking at the last of the especially common forces, which are the drag force and the friction force. These two forces are known as resistive forces, so that means they act in the direction opposite to an applied force. The first of these is the drag force, which we most commonly encounter in the form of air resistance, where we have the force due to gravity acting down and causing our cat to have a velocity downwards, and then we have air resistance acting to oppose it. And the second common resistive force is the force due to friction, with which we are quite familiar, particularly any of us that have tried to shift large pieces of furniture by ourselves. So in friction, again, we have the direction of the applied force, and we have the force due to friction opposing that. So first up, we have drag forces. And drag forces refer to the resistance of a fluid to the motion of an object through it. And I should clarify, in this definition, a fluid refers to anything that can flow, so a gas or a liquid in general. In the situations that we will consider, the drag is, in its simplest form, caused by the particles of the fluid trying to get out of the way of the object. So when we refer to air resistance, we're referring to the drag force on an object moving through air, so the resistance of the air moving out of the way of the object. For an object moving through a fluid, there are three main physical properties that will affect the amount of drag that object experiences, and they are all very practical considerations. So if you like, now would be a good time to pause the video and see if you can have a decent guess at what they might be. So the first of those properties is the density of the fluid. So the drag force is proportional to the fluid density. So that makes sense. The denser the fluid, the more particles per area, so the more particles that have to move out of the way of the object, and so the higher the drag. The drag force is also proportional to the cross-sectional area of the body for the same reason. So the larger the area pushing the fluid out of the way, the more particles have to move out of the way. And finally, the drag is proportional to the square of the speed of the object. So the faster we want the particles to get out of the way, the harder it is. So if we combine all of these relationships, we find that drag force is proportional to density times cross-sectional area times the speed of the body squared. And that gives us the following equation for the drag force, where C, or CD, is the constant of proportionality, or also known as the drag coefficient. We have quite a few reasons to be thankful for the drag force, and not in the least because it stops raindrops from being a deadly menace. So when an object, say this lovely little kitten, is falling, it's subject to gravity. At the start of its fall, when it's chased the interesting looking butterfly and jumped straight through an open window, we'll assume that the kitten's vertical speed is 0, and that means that therefore its air resistance, which depends on the speed, is also 0. So the only force acting on the kitten is the force due to gravity downwards. Owing to that force due to gravity, we have an acceleration, which means that the velocity of the kitten in the downwards direction is increased, and once that velocity is increased, then that drag force also increases. So now we have, again, the force due to gravity, but also now a non-zero drag force acting to oppose gravity. Once the kitten has been falling for long enough, gravity has increased its speed sufficiently so that now the drag force is equal to the force due to gravity. And at this point, there's now no net force acting on the kitten because the force downwards is equal to the force upwards. So that means the kitten no longer accelerates and its speed remains constant. So if we look at the equations for drag and for gravity, and we rearrange them, we can find an equation for this final speed of the kitten, which is known as the terminal speed. In this case, terminal meaning the final speed, or the ultimate speed, rather than the Terminator sense. So we'll play with these equations a bit more in the questions. Our second resistive force is the friction force. So friction is a contact force. That is, it occurs only when we have two objects in contact with one another, and we want to slide the surfaces past each other. So it's a parallel contact force. It is the bonding force between surfaces, and it opposes the direction of the applied force. So if we look more closely at the base of our bookshelf, sitting on a smooth wooden floor, we have the applied force by the man pushing, and then we have the force due to friction opposing that applied force. It looks as though those surfaces are nice and smooth, and they should slide easily past each other. But if we look closer at those surfaces on something like a microscopic scale, we can see that at that level those surfaces are not smooth, but they're jagged. So when we try to move those surfaces along each other, all the little lumps and bumps get temporarily caught, and they make our life difficult, and that difficulty is friction. So there's also a very good explanation of friction in Joe Wolf's video, which I have linked to in the resources section. Friction comes in a couple of different guises and requires a bit more of an in-depth look, so we'll look at that on the next video.